Another day, another kata. Well, a concurrent kata, of course, because I don't have already enough problems in my life. Well, today the kata is the small scale stream processing kata. We will be working with threads, actually Go routines since we use Go. We need to be faster than the fastest man alive that I showed you in the last video, right? So that's why the hat. Let's go after it. Okay, let's take a look at the instructions. Well, I never really read the instructions, to be honest, but I guess for a kata we need to know what we're doing here. So we need to design a system that handles events. Events have two attributes, client ID and UUID, which I'll explain in a second. We will get 1000 events per second, and each event takes about 10 milliseconds to process. Now, we need to design a system that adheres to the following requirements. First of all, we want to process events in real time, which means since we get 1000 events per second and each of them takes 10 milliseconds, we need at least 10 concurrent workers. The other thing is that the events with the same client ID need to be handled in order. And also, we don't want to process the event with the same UUID more than once, so we need to somehow remember UUIDs and drop events that have the same one. Okay, let's see the code. Let's start from the bottom and work ourselves up. So the first piece is the schedule. Now, here is the struct and the constructor, but the most important part is the public method. The public method, run last, is pretty much throttling the call of a function. So if you call a function 10 times, it will call it just once on the last call. And this is how it works. First of all, it spawns a Go routine right away, so this is not blocking. And it has one critical section where we check if there is already a function with that ID running. If there is, we tell that function to stop. If there isn't, or we are scheduling the same ID again, we create a done channel, we add it to the map, and then outside of the critical section, we start our pretty much wait loop. Here we either wait for done and we stop execution, or if the time passed, the time is set in the constructor of the schedule, it's this duration here, we call the function. Okay, then we have another piece here, which is a timed map. Again, data structure and constructor, but the important part are the public methods. One is a get, which is pretty much a thread-safe get on a map. And the second one is a set, which is a thread-safe set, with the additional detail that we spawn a Go routine that deletes the key after a specific amount of time, and that specific amount of time is taken care by our schedule. And with that, we can get into the bones, the meat of the system. So we have an event. I created that because I also wanted a way to check for stats, like latency, for example. We have a simple constructor here. Then the data structure that, the top level data structure, let's say, the one that we will be using, we will have separate queues, one for each worker running, and a map to take care of the UUID that we have already seen. And the constructor for the distributor is pretty simple. We spawn as many queues as C, which is our concurrency parameter pretty much. And then we spawn, for each queue, we spawn a Go routine, which is waiting for events pretty much and calling a callback with the index of the worker and the event that just got in. And how events get in is through the only public function of distributor, which is enqueue, which takes care of a couple of things. First of all, we already saw we need to drop the same UUIDs, so we have here that mechanism. We then mark UUIDs that we have seen. They take into account that this UUID seen is a timed map, so we can take care of the fact that we track UUIDs for a limited amount of time, so we don't have to clutter memory with a ton of stuff. And then we have here another requirement satisfied, which is we know that we want to handle sequentially all of the events with the same client ID. So we distribute the events with the same client ID to the same worker, which is processing sequentially. So that's taken care of for us. And of course, the other requirement that should be real time is taken care by the fact that we have multiple workers working at the same time on these events. And then we have here some statistics, not really important, and the main function, which every 10 seconds here you can see that it's printing some stats. But the most important part is the fact that we create a distributor. In this case, the UIDs are tracked for 10 seconds through the time map. We have 10 concurrent workers, and we pass F to process the events. F is pretty much just simulating that each event takes 10 milliseconds. And the last part here is that we create 1000 events every second, and we loop 100 times, so we actually create 100,000 events. Okay, so let's run this. So keep in mind we're gonna print statistics every 10 seconds, and all of the times you're gonna see are in nanoseconds. Now, we push 1000 events per second, so every 10 seconds we have 10,000. As you can see here, we are processing a bit less than 10,000 events, which means we're not really real time. And it's clear from the throughput, which is not exactly 1 millisecond, it is a bit more. And in fact, the queue length lags behind, right? Here we had 500 events that we hadn't yet processed, here 1000, and you can see that it's pretty much accumulating. But let's do something else here. We can play with this, right? So we can say, let's try with 20 workers at the same time, and let's see if we actually get into the real-time sort of situation. The cat is supporting us. Okay, yes, we're real time here. We processed 10,000 events in 10 seconds, and the throughput is actually pretty much exactly 1 millisecond. So we're good to go. And there you have it, Kata done. Of course, there's probably a ton of concurrent bugs that I left in there, right? So please let me know if I should have used less mutexes, more mutexes, less channels, you know, what you would have done differently. I'm always happy to learn from you.